Welcome back, guys. In this video lecture, we're going to talk about kinetics. So as we said, we covered in the previous chapter the kinematics of a rigid body. Now, in this part of chapter 17, we're going to talk about the kinetic equations of motion for a rigid body. Now, of course, guys, I know that if I have a center of mass G, then the sum of forces in vector form will be equal to MAG. And then if I take this equation and derive the scalar equations in X and Y, then the sum of forces in X will be equal to MAGX, and the sum of forces in Y will be equal to MAGY. Now, what if I want to find out the equations of rotational motion? If I want to do this, guys, I want you to remember that the equation of moment in vector form from statics, it's always equal to R cross F, correct? So don't forget, guys, this equation. Now, I know that if I have a dm here, which is a differential mass of an entire mass, and this dm is far from P by a distance of R, then if I want to find the forces exerted on this dm, I'm going to have some external forces represented by big F and some internal forces represented by small f. And these internal forces are the forces exerted by other dm on this dm, right? So, which means, guys, the sum of forces will be Fi big plus Fi small, and this will be equal to what? From Newton's second law, it will be equal to the mass, which is here dm, times the acceleration, which is here ai. So what I'm going to do is to take r cross the whole equation. If I take r cross the whole equation, and I know that the cross product is distributive, then this will give me r cross Fi, which is the moment of external forces, plus r cross Fi, and this will be equal to r cross dm times I, which means, guys, the total moment, the resultant moment of this dm around P, this point P, then this will be equal to r cross dm times ai. Now, what I'm gonna do is to replace this ai from the relative motion analysis by ap plus alpha cross r minus omega squared r. And then what I'm gonna do is this cross product r cross ap plus r cross alpha cross r minus omega squared r cross r. I know that r cross r is equal to 0, which means this term will vanish. And this means, guys, that mp will be equal to this differential mass times r cross ap plus r cross alpha cross r. Now, what I'm going to do is to substitute this r by xi plus yj and do the cross product. If I do this, guys, I'm going to have that mpi, which is the resultant moment for the mass dm around P, will be equal to dm times minus y apx plus x apy plus alpha r squared. What is x and y? It's the position of this dm with respect to the point P. Now, if I want to find the moment for the entire mass of the system, so I'm gonna do the sum of the resultant moment for each dm as well as the integration over this dm. So what I'm gonna have is that the sum of mp is equal to minus apx integration of y dm plus apy integration of x dm plus alpha integration of r squared dm. So let's start by this term here. What is r squared dm integration? This will be what? This will be IP. It's the mass moment of inertia around P, because this R is the position of this dm with respect to P. Now, what is integration of y dm and integration of x dm? In fact, if you remember, guys, x bar g is equal to what? X bar g, which is the position of the center of mass, is always equal to the integration of x dm over the whole mass, all right? And y bar g is also the integration of y dm over the whole mass m. And this means, guys, that I can replace this, I can substitute the integration of y dm by what? By m times x m times y bar, and this one by m times x bar. And in this case, the sum of moment will be equal to minus y bar mapx plus x bar mapy plus ip times alpha. Remember, guys, what are y bar and x bar? Y bar and x bar are the position of this center of mass with respect to P. Now, what if this center of mass is coincident with P? In this case, x bar and y bar will be equal to 0, and this will give me this equation that, if you remember, I used it in order to prove what is the mass moment of inertia physically, right? So this equation represents the sum of moment around the center of mass, and it's equal to the mass moment of inertia around the center of mass times alpha, where alpha is the angular acceleration. So the resultant moment about the mass center due to all external forces is equal to the moment of inertia about g times the angular acceleration of the body. Now, why I am saying it's only for the external forces? Because in fact, when I do the integration or the sum of moments, all the moments of the internal forces will vanish when I take the entire mass, all right? So they will be cancelled out, right? Now let's go back to this equation. I know that the sum of moment around P will be equal to minus y bar mapx plus x bar mapy plus ip alpha. And I want, in fact, to replace apx by its equation in terms of agx and apy in terms of agy, and then I'm gonna replace ip by its equation in terms of ig using the parallel axis theorem. Why? Because in fact, guys, if I want to combine the equation of sum of moments with the equations of sum of forces, I know that the sum of forces is equal to MAG. And if I take the scalar form, it will be equal to MAGX and MAGY respectively. And this means that I need the sum of moments equations in terms of AGX and AGY. So if I go back to this equation, and if I substitute APX and APY by their equations in terms of AGX and AGY, and IP with its equation in terms of IG using the parallel theorem axis, then I'm gonna have that the sum of MP is equal to minus Y bar MAGX plus X bar MAGY plus IG alpha, and this equation, as I said, is more relevant because it is in terms of AGX, AGY, and IG. And this means, guys, if I have a rigid body undergoing translation and rotation, which is the general plane motion, and I need to state the three independent scalar equations. They are sum of fx is equal to magx, sum of fy is equal to magy, and one of these two equations, all right? So guys, these two equations are dependent. You have to use one of them, and you have to use the more relevant to your problem, right? So either to use sum of mg is equal to ig alpha, or sum of mp is equal to minus y bar magx plus x bar magy plus ig alpha. Now, if you only have translation, you can say that the sum of mg is equal to 0, and this equation could be also relevant in finding three unknowns, right, combined with the equations of Newton's second law. If it makes the problem easier, the moment equation around G could be, in fact, replaced by the moment equation around a point A, sum of MA, for example. And what will be this sum of MA? Remember, guys, that at this G, I'm going to have the resultant force. And this resultant force, sum of F, right, will be equal to what? It will be equal to MAG in vector form. So if I draw this resultant force, it will be equal to MAG, right? And it will be in the same direction of the acceleration of this body. So if I draw the vector MAG, and I know the perpendicular distance from this vector to this point A as D, then what will be the sum of moment around A? It will be MAG times D, okay? So if it makes the problem easier. You can use the sum of the moments around a point that you know the distance. You know the distance between this point and the resultant force. Now, guys, if you have a curvilinear translation, remember, guys, in curvilinear translation, I have two directions, the normal direction and the tangential direction. This is not a rotational motion. This is a translational motion in a curvilinear direction. It's not in a rectilinear direction, it's in a curvilinear direction. So in this case, you can use also the tangential and normal direction, and we can state that the sum of forces in tangential direction is equal to MAGT, and the sum of forces in normal direction will be equal to MAGN, and then the sum of moments around the G is equal to 0, because in fact, as I know, there is no rotation in this type of motion. Or, as I said earlier, you can use the sum of moment around any point on this rigid body. Let's say here, I take this point B that is far from G by E in the normal direction and by H in the tangential direction, all right? So if I want to take the sum of moment around B, I have to take the sum of moment of MAGN and MAGT, all right? Now, if I take this as the positive direction, then MAGT will do a positive rotation around B, and it's equal to MAGT times E, the distance from MAGT to B, which is E. All right. However, MAGN will do a negative moment. So MAGN will do this moment, and it's in the opposite direction to the positive moment, and this means that it will be in the negative direction, and the distance between MAGN and B is H, which means sum of MB is equal to EMAGT minus HMAGN. Thank you.